can get started, being that it's 8:30. Time to get going here this morning. Thank you so much for coming, for waking up on the last day of our meeting. I hope it's been going well for all of you. My name is Alyssa Chris. I am with Syngenta in Greensboro, North Carolina, and I will be moderating the session and then also giving one of the speeches more towards the end. So just a reminder, since it's the morning, everyone grab your cell phone and make sure it's on vibrate. If you've got multiple cell phones, make sure they're all on vibrate. I've made that mistake before. So check them all out. We all know that, we don't want to have any photography. I think all of us have allowed our presentations to be recorded and used later, so no need to take photography of anything here today. So our title is Climate Cycles, Climate Forecasting, and Disease Cycles Spanning Multiple Years. I'm very excited about our first two speakers. We're going to start with George Taylor, then have Clyde Frace, and then myself, Alyssa Chris. So with that, I would like to start by welcoming George Taylor. He is the current president of Applied Climate Services in Corvallis, Oregon, and he is the former state climatologist of Oregon, and where he served for 19 years. So I know I'm looking forward to learning some climatology. Here we go, George.
Cool. Good morning to you. I was warned that you would be kind of a small group, but that's okay. I'm sure you're enthusiastic and a lot of fun, and I'll try to be all those things too. Yes, I'm George Taylor. I am also a certified consulting meteorologist. That's the certification that they give you when you're a meteorologist and have been doing it for a while. I want to define weather versus climate, and this is pretty much a dictionary definition, but I have a couple of definitions I like better. Basically, weather is the state of the atmosphere at any time, a given time and place. Right now in Pasadena, it's whatever temperature it is, and it's sunny, and other places it isn't. But then climate is weather averaged over a period of time. There's an average term that we use called normals, and typically a normal is a 30-year average, and it's been standard in climatology for a long time. But there are two other definitions I really like better. The first one came from a second grade girl. I was talking about my job in a first and second grade class, and I asked the children, I said, well, I'm involved in climate, which is related to weather. Do any of you know the difference? And the answer I got from a little girl named Amy is, well, Mr. Taylor, weather is what you get and climate is what you're supposed to get. And I got written permission to use that from Amy, so it's not copywritten or anything. But there's another one I like too. I was teaching an online class at Oregon State University, where I was for a long time. And on the first homework assignment for this introductory class, I asked the students that same question: define the difference between weather and climate. And the answer I got from a young lady was, well, climate tells me what kinds of clothes to buy and weather tells me what clothes to wear. I thought that's pretty good and practical as well. So I want to talk first of all about long-term climate changes, and I'm going to talk about climate at various scales and locations and try to pin down some causes and effects and do all that in half an hour. So see what we can do. This is a chart showing estimated temperatures from ice cores for the last 2.4 million years. And what you see here are basically cycles of warm periods and cool periods through the whole record. A lot of this is pretty sketchy because ice cores are not always easy to interpret, nor are they necessarily consistent. If we look back at just 450,000 years, we see the same kind of thing at a different scale. Basically cycles of interglacials and glacial periods. And over that period, the interglacials have been relatively short compared to the ice age periods. And you can see where the modern day temperature is kind of in the middle, maybe a little bit above the middle. And then the various forcing mechanisms, like in the middle graph, greenhouse gases, and showing the correlation with the surface albedo or reflectivity. On the top, CO2, methane, and sea level. Again, all three correlating quite well. and then at the bottom, calculated temperatures. So I look at these and I see cycles of various lengths, cycles superposed on cycles. Some of the causes of long-term changes are listed here, and you can read them. But I'll talk about them one at a time. First of all, this is Milutin Milenkovic, a Serbian scientist who did a lot of study of cycles, especially having to do with the Earth, Sun, and solar system geometry. And he identified 3 different cycles that affect the Earth. And one is the 95,000 year cycle that's from eccentricity. The eccentricity is basically how circular the orbit of the Earth is around the Sun. The one on the right is greatly exaggerated just for effect, because it's nowhere near accurate. But during the kind of wobble period on the right, there's a more elliptical orbit of the Earth around the Sun. Obliquity is the second one, and this is 40 to 50,000 years, and it has to do with the axial tilt. The Earth's axis is tilted at about 23 degrees, 23 plus right now, and it can vary from about 22 to 24 and a half. And the third is precession at 25,000 years, which has to do with the Earth's rotation itself rather than its revolution around the Sun. So all of those appear to show up in the data record, but I want to emphasize that the data record is often sketchy and a lot of implications. So, but the geometry seems to be evident. And then if we look at the more recent past, this is 10,000 years, and this is from Greenland ice cores. And again, what you see, as we did in the longer record, was a cyclical thing with warming. Since 0 AD, there's been the Roman warming, the medieval warming in about 1,000 years ago, and then the modern warming. And you see the modern warming is pretty small compared to some of the earlier ones. This is the last 4,000 years, and the present temperature way over on the right. And just to the left of the present temperature, there's a cool period known as the Little Ice Age. Then you see the medieval warming at about 1,000 years ago or so. And that's where we are in the last 4,000 years. The Little Ice Age was a very, very significant event. And in terms of society, cold periods have always been detrimental, more detrimental to commerce, to life, especially to agriculture, than warm periods have. So the Little Ice Age, which lasted 400 or 500 years, was disastrous in a lot of ways. This is a chart from Hubert Lamb's book, Climate History in the Modern World. World is misspelled, but ignore that part. But his chart is based largely on anecdotal information and reports on the ground and crop failures and things like that. But his estimate was that around 1,000 to 1,300 AD, there was a very warm period, and then it got a lot cooler. And there's a lot of evidence that it really was cold, not just in Europe where most of the records were, but all over. And then since then, there's been a gradual warming, and we're kind of in the ballpark of what temperatures were like 1,000 years ago, according to Lamb. This is a piece of information which backs up what Lamb said, and this is tree ring widths of bristlecone pines in the White Mountains, and with the assumption that the width of the tree ring is proportional to temperature. It's not necessarily that simple, because it certainly is affected by other variables like moisture, but there does seem to be a correlation, and it matches up very closely here in California with what was reported by Lamb, mostly in Europe. Here's another similar tree ring data set that shows pretty much the same thing. Now, possible causes of the Little Ice Age are, first of all, the sun. And And one of the things that scientists know is that sunspot cycles really affect climate in a big way. Generally speaking, the more active the sun is, the more sunspots there are, the greater the solar radiation, and all else being equal, the warmer the temperatures. So there was a period from about 1600 to 1750, known as the Maunder minimum, where the sun was relatively void of sunspots. And there were several years without a summer during that period, a lot of crop failures, a lot of problems. At the same time, people were ice skating on the Thames River, and that hasn't happened for a long time. Since then, there was a minimum in about 1800 called the Dalton minimum, and now we're looking at modern sunspot cycles that have been very active until the one we're in right now and the one before. Both of the current and the previous one have been much quieter. And there are a lot of scientists, especially those in Russia, who are predicting that we're going to be moving into a period with fewer sunspots for multiple decades and therefore cooler temperatures than we'd have if the sunspots were average. I'm just going to skip that one and say the next thing is volcanoes. The major effect of volcanoes on climate has to do with large eruptions of tropical or subtropical volcanoes producing a lot of dust. And two examples of that would be El Chichon in Mexico in 1982 and Pinatubo in the Philippines in the early 1990s. Both of those were large tropical volcanoes with a lot of ash in the atmosphere. They reflected sunlight and caused cooler temperatures. And this is the chart showing volcanic eruptions. There were some really big ones way back in the record. Like, I think it's this one right here is, no, it's this one, Toba, one of the Indonesian volcanoes. A lot of these are, but each of those caused a significant cooling of the atmosphere following the eruption. The tropical Pacific. To me, if there is a so-called smoking gun when it comes to at least short-term climate effects, it's the tropical Pacific. This shows the three different charts of the tropical Pacific, the equator there in the middle. Here's Central America, South America, New Guinea, Australia, etc. And then these are color shaded according to sea surface temperatures. What you're looking at here is often called the Pacific Warm Pool. It's a large area of rather warm water, in some cases very warm water, and this is the most significant, the largest source of terrestrial heat of any place in the world, right there. And because it's the biggest source of terrestrial heat, the changes in the sea surface temperature distribution cause profound changes in weather and climate everywhere in the world. This, to me, is where just about everything begins. And we have really three different phases that we identify. The one in the middle we call normal or average. Probably normal is a bad term, even though it says that here. So ignore that, and let's just say average conditions. On average, there's a cool current coming up the coast of South America from Antarctica, and it's intensified by the fact that the winds in the tropics the trade winds are from the east, and they literally push the water away from the shore, causing upwelling near the coast, and that upwelled water is cool but also very rich in nutrients. And so this area, Peru, Ecuador, northern Chile, tend to be really good, very productive fishery areas. A lot of fish because of the nutrients in the cool water. But there are two extreme phases, and one of them is called an El Niño. During an El Niño, what we think happens is the trade winds that have been blowing and pushing this cool water away from the coast suddenly die or even reverse themselves, and literally the water sloshes back towards the east, towards the west coast. And what you see here is during the El Niño, during the average year, here's the cool often called the cool tongue coming out from the coast, but warming as it crosses the vast Pacific, and then finally reaching temperatures in the 80s or so, maybe 85 degrees out here. But when the trade winds die, that water pushes back this way, and what you see in the El Nino chart at the bottom is yellow and orange here instead of blue. And if you look at all of the yellow and orange in the whole Pacific and compare it with that, there's a lot more yellow and orange here. In other words, the average temperature of the Pacific is much warmer during an El Nino. Now, the counterpart to El Nino is usually called La Niña, sometimes called anti-El Nino or El Viejo. It has lots of names, but I like La Niña. And a La Niña is a lot like an average year, but it's more intense. You see a lot more blue in here because the trade winds are stronger, the currents are stronger, and you get a relatively small area of very warm water over here, but a lot less area than here. So during an El Nino with all this warm water, there's a great deal of heat released to the atmosphere and a lot less during La Niña. This is my single favorite chart, and it's kind of busy, so bear with me, but I think this is a really important one. This shows two different time series, the red one and the black one. The black one is the Niño 3.4. It's an index describing whether we're in an El Nino or a La Niña or neither one. And that's plotted over here on the right-hand side. So a zero value right here would be an average year, or neutral, as we sometimes say, neither El Nino nor La Niña. Sometimes we call it La Nada, the nothing. But the positive values here are El Nino events, and the negative values are La Niña events. So this is the records that we have on that go back about 100 years, a little over 100 years. But we have another data set here that to me is the best and the most representative temperature data set we have. It's temperatures of the lower troposphere recorded from NASA polar orbiting satellites. They have an instrument called a microwave sounder, and they're able to measure the temperature in the atmosphere. And the lower troposphere is about the lowest 10,000 feet of the atmosphere. It's where people live and most activities go on. So this is a plot of both of those back to when the satellites began in 1978. And so if you look at this, of course, you see these are marching pretty much in lockstep with one another, suggesting that there's a strong correlation between them. And if I look at that, I see one of them appears to be happening first. Like right here, the black starts going up, and then later on the red follows, and then the black goes down and the red follows. Pretty much all the way through, it looks like the black is leading the red. And remember, the black is Niño, and the other is the satellite temperatures. What this suggests to me, and oh, by the way, the magnitude matches very closely too. This is adjusted so that the overall magnitude would be similar or the same. But there are two exceptions to this. And this, to me, is that the lower troposphere temperatures are a function of, directly proportional to, changes in El Nino and La Niña. But there are two exceptions, and one of them is right here, where there was an El Nino, but right here's an El Nino, and the temperatures in the lower atmosphere stayed relatively low. Here's the El Nino indicator, but the temperatures only went to there. And a more significant one happened here in the early 90s when there was an El Nino, but temperatures actually went down. Now, both of those were large volcanoes. I mentioned both of them, El Chichon and Pinatubo. But what this chart says to me is that we can assess, correlate, maybe even predict the temperature of the lower troposphere based almost entirely on El Nino and La Niña, the tropical Pacific, plus volcanoes. If we knew those two things, we pretty much know what the temperature of the atmosphere is going to be, and those seem to be the two most significant variables affecting the temperature. There's another long-term kind of thing that's related to El Nino and La Nina called the PDO, or the Pacific Decadal Oscillation, which not only is flip-flopping in the tropical Pacific, but in the North Pacific and some of the other oceans as well. And there's a similar thing in the Atlantic called the Atlantic Multidecadal Oscillation, or AMO. We're finding more and more correlations like these as we get better and better data from buoys and satellites and so on. But here's a chart of the Pacific Decadal Oscillation back to 1900. And essentially, the reds show the positive PDO periods coincide with El Nino events, and the negative with La Niñas. So just think El Nino red and La Nina blue. And you notice, first of all, from about 1900 to actually early on in the record, there was about an equal number of reds and blues. But beginning about 1920, we went into a period of about 25 years with a lot more red than blue, a lot more El Niños than La Niñas. And in fact, this was a period when global temperatures were quite high. This was the warmest decade in the US, the warmest decade in California, the warmest decade in Oregon, where I live. Lots of places had their warmest decade in the 1930s, and not coincidentally, I think, it was a period with positive PDO caused by a lot of El Niños. But something changed in the late 40s and early 50s, and we moved into about a 25-year period with a lot of blues and not much red. And this was much cooler globally. It was cooler here. It was cooler in Oregon. It was cooler not everywhere in the world, but in a lot of places. And then we moved back in the 1970s after a period when people were talking about global cooling. And then we moved into a period with a lot of El Niños again. And of course, this is a period when a lot of people were talking about global warming. And it was warmer in the US, it was warmer in California, it was warmer in Oregon, it was warmer in a lot of places. But then we switched back again in about the year 2000. And since then, there's been a kind of an equal amount of red and blue. Not quite as concentrated as it was back here. And I have a few time series to compare. This is where I live, Corvallis. This is one of the best long-term stations in the U.S. We have data back to 1890. And this is the annual average temperature showing a spike in the 1930s. The warmest year was 1939. 34 was a very warm year. And then it dropped down, and then it came back up, and then it's dropped down again. But notice how closely it correlates with the PDO. The red here coinciding with warmer, blue with cooler, etc. If we look at precipitation, we see the same kind of effects. Now, in Oregon, El Niños tend to be warm and dry. In Florida, they tend to be warm and wet. And in California, they tend to be warm and wet. So it depends on where you are. But this kind of chart is pretty easy to create for any place that has long-term data, and I'm not going to say much more about it. Arctic temperatures see the same kind of effects that El Nino periods. This is Arctic temperatures, surface air temperatures north of the Arctic Circle from Igor Polyakov, and this red period down here coincided with the warmest decade, the 1930s. Measured in the Arctic, and 1937 was the single warmest year. Now, here are some weather forecasting applications. This is a chart of maximum daily precipitation at Corvallis versus the PDO. In a lot of ways, this is typical of the kind of forecasting we can do with climate data. It's a mess. Is there any kind of a correlation there? Well, there's not really anything like a linear or sinusoidal correlation, but what we do see with El Niños, and this is evident in Oregon and many of the other states, is that the extremes in rain, in temperature, and in snow tend to occur in about the middle of the distribution. Notice how if we have the 5 wettest years that Corvallis has ever seen, This was the one in 1996, and this is 65, and anyway, doesn't matter. But the biggest extremes tend to occur in the middle of the distribution during the neutral or the average PDO periods, and then become increasingly rare as you drop off this way. So all that says is that if we have a neutral year, we have an increased chance of an extreme rainfall event. This is another one, and this is related to one of the key agricultural areas in Oregon. This is the Hood River, which is a very productive fruit and nut and other crop place in northern Oregon near Mount Hood. And one of the real bummers for them is if they get either a hard freeze or even just a freeze in the spring. If the fruit is already set, it can ruin the whole crop. So they really care about the last state, in this case 32 degrees. Often we look at 28 or 24, but what you see here, now these are La Niña years over here, and these are El Niño years over here. And this is just a simple linear correlation. We get an R squared of about 0.24. So 24% of the variance. That's pretty pitiful if you're an engineer. But with climate, that's about as good as we can do. And what this, of course, says is that during a La Niña year, you have an increased chance of a late spring freeze. And during an El Niño year, you're unlikely to. And there are certain decisions that growers can make based on that. How am I doing for time?
About 5 minutes.
Okay. I just found this yesterday. This is pretty cool. This is a chart of by climate division. These are all the different climate divisions for different states. Right now we're in this one, but what this shows is the summer precipitation during a building El Niño. Right now we're in a phase where an El Niño is developing in the tropical Pacific and is expected to strengthen and be a really big one when it's done. And so this shows that the yellows are places that are somewhat dry during the summer, in other words, right now, and then the green show the ones that are wet. But these are just barely above zero, so it doesn't show a very strong correlation. But this is a kind of analysis. It's not that hard to do. There's NOAA ESRL has a website where you can create your own of these. You name the years and the months, and it can create it for you, so it's pretty cool. Future ain't what it used to be. Thank you, Yogi. I'm going to skip that one and go to, no, I don't want to bother with this. This is all going to be shown and recorded, so you can go back and look at these charts. But does anybody recognize that guy in the picture? He used to be the vice president. It's Al Gore, and he gave a lot of talks, and he talked about the correlation between carbon dioxide and temperature, and he showed that they vary very much together. They're pretty much in lockstep with each other. And here's CO2, and if it goes way up here, the implication is this is going to follow. So he's saying CO2 is the cause of changes in temperatures. There's been a lot of scientific literature which has shown that CO2 changes have always followed temperature changes, and it's mostly because of the oceans. That when the oceans warm up, they release CO2, and when things cool off, CO2 is absorbed much more readily. So the oceans seem to be the dominant factor. Here are just 4 examples from journal articles. The top one, CO2 lags behind by about 1,200 years, 600 years, 1,900 years, 800 years, and so on. The future. The models pretty much say that temperatures are going to go up because they're very much driven by CO2 concentrations. Here's the actual temperatures for the last 100 years. And this is from that set of satellite data. And this is, no, I'm sorry, this is not 100 years. This is back to 1978. But here's again that blue period of negative PDO, positive PDO. And since about the year 2000, temperatures haven't risen significantly. Some people call that the pause, and they're saying it's going to start up again, and who knows. These are the model predictions from the IPCC, Intergovernmental Panel on Climate Change, and here's the satellite data and the balloon data, not going up much, if at all. This is the dominant climate response to CO2 from 49 different models, and here's what's really been happening. Back to Greenland, the last 10,000 years, there's a downward trend, and I think I can safely say that in the next 10,000 years we're going to see much cooler temperatures because the trend is certainly in that direction. And eventually the interglacial will end and it'll get really cold. Now I want to show you one other thing, and this is a wonderful data set that I may be introducing you to. Maybe you already know about PRISM data. PRISM is a software program, but also an organization at Oregon State University that was founded by Chris Daly, my former colleague. And what Chris has done is taken surface data for over 100 years and made monthly data available. Monthly, in this case, this is 30-year average annual precipitation. Very, very detailed, down to a scale of less than a kilometer. Gridded data that you can get for free at prism.orst.edu. Short and long-term climate patterns, lots and lots of stuff in map form or GIS. That's just an example of annual precipitation in western Oregon where I live. I live right about there. So color shaded map. And again, that's 30-year average. This is average maximum temperature for July. Average minimum for January. Average daily minimum temperature for January of 2014. This was January of one of the big, very cold upper Midwest years that had the so-called polar vortex, and you can really see it in there. And that's the normal minimum for January. So see the difference? Like especially that magenta blob, right here it's over Minnesota, and here it's down clear into Illinois. So it's interesting to be able to compare different years like that. And that's 1996 annual precipitation, one of the wettest we ever had. And that's the end. And if there's time for questions, I'd be glad to
one quick question,
take one quick question.
With your chart of El Niño and so forth, it looks like the average we're never at the average.
Good point. And I was discussing this with Clyde, with the next speaker. You're right, it doesn't tend to linger in the middle. And one of the things that we thought about is that the reason that we tend to get the extremes during those neutral years is maybe because it's in a transition, that it's not stuck, and it never gets stuck. It just kind of goes back and forth. So yeah, good observation, and we've noticed that, and we're trying to figure it out, but that's the best explanation I have for why those extremes occur.
Thank you very much. I am hoping to also have some time at the end for additional group questions, and then of course all of our speakers will have time after we're finished. So our next speaker today is Clyde Frace. He is a professor in the Agricultural and Biological Engineering Department at the University of Florida. He is also part of the Climate Extension Program under the Southeast Climate Consortium. So welcome, Clyde.
Thank you, and good morning, everyone. I don't know if this was planned, but I really like the fact that George gave this talk before, because as you can see, there's a lot of information available, a lot of knowledge, but the question is, how do I use this knowledge, this information in agriculture? And that's exactly what we try to do, is to translate that knowledge into something that can be used for decision making. So I think it was really good. Anyway, I'm here to talk about this strawberry advisory system, but what I want to do is, before we get into the SAS, as we call it, we will give you an overview of the agroclimate program. The strawberry advisory system is under a larger program that deals not only with crop diseases, but also other issues. And so I want to kind of give you an overview, so I think it's a much broader view of what we do. I also want to recognize Natalia. Natalia Perez is the plant pathologist working with me under this system, and basically the brains behind it. So I just follow her. And well, with that, let's get started here. I don't need to say that climate is a major factor in risk factor for agriculture, and most of the time, we're dealing with too much rainfall or too little rainfall during the season. Sometimes it's not the amount, it's the distribution that matters. Sometimes it's just a weather event like a hailstorm, or in our case in Florida, hurricane before harvest that can bring a lot of losses. But also climate can be favorable for diseases, as you all know. So it's a major issue for ag, as we all know. So like I was saying before, this agroclimate program is really, what we try to do is to put this information, data, the knowledge about the cycles that George was just talking about, and how do we translate that into something that can be used for making a decision. And that's really, in a nutshell, all that we do is to put together this information in a way that can be used for reducing risk, for increasing resource use efficiency, and ultimately we want to increase the profitability of the farmer. I had a vision, like we put together this vision back in 2009, I believe, about this, what we call the agroclimate services. And at the beginning, we really started focusing a lot on the seasonal climate variability because of the cycles that we have in Florida, especially the El Niño, La Niña cycle. But it was clear to me that when you start talking about this, you go meet with farmers, the first question they're going to ask you is, so what's going to be next week? So they're very interested in the weather, of course. And so I realized quickly that you don't want to just talk about one thing. You have to bring the whole time frame into perspective, because some of them are curious, in fact, even about climate change. But I can tell you for sure that if you go talk about climate change with farmers in Florida or in many other places, your audience might be very, very limited. I mean, they're curious, but it's not, ultimately they have to be in business next year, so it's difficult. The other thing is that we learn also that when we start talking about adaptation strategies for the next season, it's pretty much a way that you can start talking about adaptation, long-term adaptation strategies as well. So it's a good exercise to bring the concept of the adapting to climate into perspective for them. And of course, the weather is very important as well. So when we're talking about decisions, it's pretty straightforward that farmers use the weather forecast, and we all know that. They certainly look at the TV most of the times, or looking at their cell phones nowadays, and they really decide about basic operations. Should I be planting tomorrow? Spraying is a big one. Our conditions are going to be okay. Fertilizing, irrigation, those are straightforward decisions that they keep track based on the weather forecasting, which is for the next few days. Cold protection is a big one for us in Florida. Cutting hay, you don't want to cut hay and then have 5 days of rainfall after that, decreasing the quality. So when we're talking about the seasonal climate outlook, those are more like strategic decisions, and it's not so easy to make those decisions, but basically we can anticipate that if there is a, let's say, an increased chance for below average rainfall, you may want to rethink what crop you're going to be planting or what variety you may be planting. You may want to change your acreage allocation. You may want to look at planting dates. Crop insurance is a big one, of course. You may want to increase your coverage or decrease based on what you hear for the climate and during the next season. In Florida, in North Florida particularly, there's a decision that they have to make every year. The livestock farmers is they're going to invest more in winter pasture, or they're going to buy more feed. And this is one that can certainly be tweaked based on what you expect for that season. If we're talking about diseases, of course, there are certain decisions there, like if you are predicting a very wet season, very problematic season, maybe you want to check your variety. In the case of peanuts in Florida, for instance, we had to switch planting dates because of tomato spot wilt virus. That was a problem if you plant earlier. Spraying, of course, is not a matter of just go, will I be able to spray, but is it the right time to spray as well? That makes a good sense to look at the climate conditions. So, with that in mind, also I thought about all those different time frames from real-time monitoring all the way to long-term climate projections. And in my mind, you have to combine, if you want to be successful, you have to combine education and service. So you have to provide a service, you have to provide the information, but also you have to look at the education aspects. And it's clear that as we move to long-term climate projections, even or with the cycles, you have to ramp up the education process. But of course, in the service side, we provide more service just tracking what's going on now, and then looking at long-term climate projections, which are much more related to what we need to do in terms of education. I also think that the way you deliver the information is very important. And of course, if you are looking at today, next few days, you may want to have this information in a smartphone. Obviously, you don't see a farmer running to look at the smartphone to see what's going to be the climate projection for the next 100 years. I mean, they're more interested in what's going on now. So you don't want to deliver any kind of climate change information in your smartphone, I think. Most of what we do is related to this, what's now to the seasonal variability. That's where most of our solutions are. So with that in mind, I just want to, I'm glad you already introduced the topic so I don't have to cover it. But El Niño, La Niña is important for us in Florida. In the southeast U.S., we are affected by those cycles. And I can skip this, but you already understand the Pacific, the sea surface temperature in the tropical Pacific does affect our climate, not only in the southeast, but in many other places. The jet stream patterns change during El Niño. You have a reinforcement of this Pacific jet stream. It's a subtropical jet stream pattern because of the increased convection, the warm pools in the Pacific there. And we have more rainfall in the southern U.S. In fact, this potential El Niño that we are pretty much sure it's going to happen now, it's supposed to bring a wetter winter and spring for us in Florida. So what? That's the question. And if we're looking at our strawberry capital of the world, which is Plant City, Florida, if you look at long-term average of rainfall, monthly rainfall, starting here in January, going all the way to December, the anomalies during the El Niño, you can see that in January, February, March, all this time we have normally above average rainfall. You can see that August, September, we have a below average. And we're talking about averages. You can look at distributions if you want, but just showing the averages here. And during the winter time, or starting to get into the winter time, we have again above average rainfall. So this is caused because of this El Niño pattern. Well, guess what? When is the strawberry season for us? It starts in October, goes up to March. So what can you conclude based on that? It's going to be a wetter season. So you're probably going to have more disease problems. You do have, El Niño does not tend to favor hurricanes. So you can see that in this August, September, you're going to have below average rainfall, most probably because we have less tropical storms during that time of the year, during El Nino years. So this is an important aspect for us. If we look at the La Nina typical jet stream patterns there, they're going to be above, north of us, so we have warm and drier winters and springs. And of course, this, if we go back to Plant City now, and this is one of the tools that we have. In fact, you can look at this for several weather stations in the southeast. You can look at your local effects. You're going to see now that we have below average rainfall during this spring and the winter time. And you do see some increase in the hurricane activity, in fact. Although most of the increased hurricane activities occur during neutral years. But what does that mean? Well, it means that you can perhaps, what we have already showed, 50% less sprays during La Nina years with no problems with the quality or disease control. And we have seen that already. So if you consider what they do normally, which is apply every week, we talk about 10 less sprays during the season, which is significant cost reduction there. Well, we model leaf wetness. Unfortunately, we don't have leaf wetness data going back many years. In fact, we don't have, even today, many records of leaf wetness. So we model that, and if we look at, maybe kind of hard to see, well, at least in my screen over there, it looks a bit better. But during El Nino, you can see that you have, using this model, dew-point depression, we can see that on the median, it's above what we will have in La Nina or even during neutral years here. So what does that mean? That this is favoring more fungal diseases in our situation there. So this is the main page for agroclimate. Now I'm going to just give you a brief introduction of the whole system there. We have many things in tools and forecasts and management fact sheets, suggestions. We also have the current phase, which is an El Nino. Don't look at this. We provide this forecast for the next 3 months based on the IRI. This is outdated already. We have a much higher probability for an El Nino during the last 3 months. I think it's 98% now. We track those cycles because they are important for us. MEI is basically an El Nino index, and you can see when it's red, it's El Nino, blue would be La Nina. When it's, it doesn't mean that it's always El Nino here. It has to be above a certain threshold. NAO is a different cycle that for us is important in terms of temperature in the winter time specifically. So we do track that as well. The tools that we have are many. It can be map-based, it can be weather station-based, it can be based on 15-minute data, it could be hourly, it could be daily data sets that we need, it could be real-time, it's just historical in some cases. Maybe we use crop models, we use some other disease models, or just simple statistics. One of the tools that we have, I'm glad you talked about PRISM. I mean, we really like that data set. It is very useful to us. It's a 4x4 kilometer grid. We get it daily, in fact, now. Although they process after 6 months, they kind of reprocess that. But you're looking here at the last 30 days, a couple of days ago, what happened in our region. This is the total rainfall. This is the anomaly. I'm sorry you can't read that. It's too small. But what it's showing is that those are Strawberry County, in fact, Tampa area here is getting a lot of rainfall. And I was just looking at your building summer, building El Nino chart, and it did show increased rainfall in this area. So it's interesting to see that. I didn't look at the other places, but certainly showed increased rainfall in this area. And we are kind of below average in this area here in Miami area. But that's very useful. It's a general tool, but it's kind of really useful. Now, going to the strawberry itself, we grow about 10,000 acres every year. It's 15% of the U.S. total production, but about 100% of the winter production. And fungicides are a larger proportion of the cost, about 15%, and normally they do calendar-based applications. So we're talking primarily controlling anthracnose and botrytis here. The implementation of this system took a lot of work by Natalia, looking at different thresholds, testing the model. We implementing weather stations where we're not covered well by the existing mesonet that we have in Florida. A lot of calibration. Leaf wetness sensors are not easy to work with. We have to calibrate them. In fact, in our system now we use 2. We just don't trust them enough to just use 1 leaf wetness sensor. And when both are dry, it's dry. When both are wet, it's wet. Many times one is wet, the other is dry. Then we go to the models to decide if it's wet or dry. I'm anticipating that in the future we're just going to be working with the models and move away of the leaf wetness sensors. This is the system. How it works is fairly simple. Those are the weather stations that we're tracking now. The risk levels are given to you by green, yellow, or red. If it's red, it's high risk. If it's green, it's low risk. Yellow would be moderate risk. So if you can look at this tool now, you just see, oh, okay, here I have a high risk situation. Here's okay, here's depending on what. Well, once you know that, you can click in a given station and it will kind of give you more details, but you can also click and view recommendations here. So the recommendations, you have to go through some quick questions. When is the last time you applied? What did you apply? Et cetera, et cetera. Then the system, of course, goes into this decision tree in the background based on what you supplied in terms of information. And with that, you can get a recommendation. So that's basically it. It's a 5-minute introduction. Farmers can use that. They really like it. And there has been, I think that we can safely say that over 70% of the acreage in Florida now use this system to decide about fungicide application. You can look at the simulation of the infection index. We can use 2-day forecast as well. It's a lot of information. You can look at the we use 15-minute data interval for this one. You can see when it gets dry, get wet, etc. So there's a lot of detailed information in the background. If you are interested, you can look at this. And you can also subscribe. You get an SMS or you get an email. And that's exactly the tool that got me into the cell phones, because farmers, after a while, they don't look at this anymore. They just look at the SMS. And that's all they want, because they say, oh, I know what to do. Just tell me if there is a situation or not. And that's all I need. So I said, well, these guys really like the cell phone. So they wouldn't do much. So we decided to invest on that and become more proactive in terms of developing tools that are for smartphones. And we focus on 3 main topics. There's disease, and I call it enhanced weather information. It's more than just weather and irrigation. And just to give you a quick introduction, this new version we have for the strawberry system, it's available for iOS and Android. And it's very much like the web-based, but in a much simpler way. You have the same kind of initial screen. You can click on a given station. It will give you more details and the recommendations. So you can look at this. You can scroll horizontally and get the last 30 days, the 2-day forecast here. Also, you go through the same questionnaire and you see what answers based on that. You end up getting a recommendation. So it's very simple. This one is a 30-second introduction. That's what I want. I want something that we can show in 30 seconds, 1 minute, how to use it. The farmers get out of that place and they are ready to start using the system. What's next? Well, we're expanding with Guido now from Clemson University. We already, you can't see it here well because all the stations that, when the day I got this screenshot, they're all green, no risk or low risk. But we're expanding to other regions. Natalia has a couple of other projects where we're going to go beyond South Carolina. The other thing I'm very interested is in start looking at the grid-based information. Of course, it comes to the question of temporal resolution. Grid-based products like Prism, you get daily. Daily is not going to work, right? So we're working with NOAA, and we're trying RTMA, real-time SSK analysis data. That's hourly. So we're getting to hourly simulations. We need to look at their models for leaf wetness and see how we're in the process of looking at the spatial and temporal issues using gridded data to provide the maps for disease risk levels. And I think the future, we're using PRISM for ET, evapotranspiration estimation, all based on temperature only, or using simulating solar radiation with Bristol Campbell, for instance, and see how can we bring this information out to a larger, broader audience, because when you are just working with the weather stations, you are restricted to the area just in the vicinity of the weather station. And rainfall is, of course, the main issue. So I think that's where the future is going to take us, a lot more of grid-based products, but they require more work to make sure that we are providing good information. So with that, that's it, Alicia. I think I got some 5 minutes. But we can all get together and have a discussion at the end too, if you prefer, which could be good. Yeah, up to you.
I see if anyone has a pressing question right now, it's fine. Anyone has one?
Yes. They are receiving the information. The preference for the method so far as I know, the apps are fairly new. The SMS is the way they really like to see that. Natalia can talk more about how they are using this, but what we know is that some farmers that at the beginning, they tried the system in a spot in the field, they reserved a little area to try it. And nowadays, what's happening is the other way around. She wants some of the farmers to leave a little area with the traditional calendar spray to check how things compare, and she's having a hard time with that, so because they trust. I think the key question, the key word is trust. And of course, it's a very expensive crop. They will not risk it until they believe your system. And the only way they're going to do that is by trying a little corner. And if you get them to do that and they see the results, I'm pretty confident. I can almost see almost 100% of the acreage on this system. The only limitation we have now is what? Is the limitation of the weather station. And we are very concerned about having farmers. Farmers are buying their own weather stations. It's happening everywhere. They're very inexpensive weather stations. And the concern we have is that some of them come already. So I want to add my weather station to your system. I say, let me look at your weather station. I go look and say, oh my God, I don't want that one. Because they don't calibrate, they don't maintain. I have seen weather stations with leaf wetness sensors on the ground, just laying on the ground. So we got to be very careful because ultimately we are playing with the credibility of the system. So we have to be careful with the source. Yeah, but that's the only concern I have, to be honest. I think they're ready for this. Yeah. Thank you.
Any other questions right now?
Thank you.
Mechanical measurement of leaf wetness is a intractable problem. Is it possible to estimate leaf wetness from other more easily measured parameters using energy balance models?
Yes. Yes, indeed. Oh, wait, I have a paper. We have a paper coming out on this. It's an interesting question because we have several different models. There's one more mechanistic model, the latent heat flux, for instance, the Pennamonteith based, and it's very good, but it's based on what? Solar net radiation, wind speed, relative humidity, temperature. So what we found out is that you have a very good method there, but you depend on the accuracy of those sensors as well. So if you have a very good, relative humidity is key, and many times you see the weather stations with relative humidity plus or minus 5, even worse than that %, which means that if we use this good method with sensors that are not well calibrated, you're going to end up with bad results. So maybe it's preferable to go to a simplistic methodology. I'm not in favor of just relative humidity thresholds. I don't think they work very well. But CART, dew point depression, so those are the ones that I think that dew point depression overestimates sometimes, but if we're going to be wrong, we better be wrong on the safe side. So it's a trade-off. Definitely, I think that we can do a better job. With some of the leaf wetness sensors that I have been testing, it's better to use a model. I trust the model better. So yeah, it's a big issue, and we have to work on that. And maybe we can come up with look at different ways to look at leaf wetness sensors as well, different ideas. I think there is an open area for research there. Thank you.
I guess, well, somewhat awkwardly, I'm introducing myself for the next one. So, as I said at the beginning, I know many people have come in. I'm going to talk briefly for about 15 minutes and show you some work that actually started when I was a graduate student at The Ohio State University with Pierce Paul and Larry Madden. I'm hoping then, too, if we have time for some more group discussion and questions about the idea of using these climate patterns and how, in some more practical, pure practical ways that in the next few years we might be able to make changes as we move to the future, whether that be in models or just how we go about some of our business and our research. So with that, the general title of mine is Using These Climate Patterns in Prediction of Fusarium Head Blight Epidemics. But in all honesty, I'm going to talk about two different diseases today. One being Fusarium head blight, which I'll abbreviate most of the time through this as FHB. The other one being Saganaspora nodorum gloom blotch. And for both of these, if you've been in some of my talks before, you may have already noticed this, that with the great past people at The Ohio State University have always been taking data on these pathogens and on others. And now we are up to 51 years worth of a relative rating scale for both FHB and SGB. And if you want details on how that came about and exactly how that's done, I do have a citation for a paper that has many details about that for you. So I'm going to be using both of these as we go through and show how we use climate patterns to relate to these patterns that we saw in disease in Ohio over time. So the first thing you should know is, again, this started back for me when I was a graduate student. So it was about 2008. And I kept getting told, Fusarium head blight is highly sporadic. That word, we write it in a bunch of papers, we say it all the time. It's highly sporadic, it's highly sporadic. And a lot of that, of course, has to do with the local weather conditions around the time of anthesis, and that's been proven, and there's several excellent models to that point. But I wondered, and we all wondered, I think, if there's another underlying mechanism as to how the sporadicness was happening. So I just want to show you the last couple of years, by the way, in a few different maps. So I've got the first graphic up here that I already showed you. This is over the 51 years. I went ahead and pulled some numbers off that graph from 2002 to 2010. And these are just ratings from 0 to 9. And now the graphs I'm going to show you down here, I'm going to keep going through a few more years. And I just want you to sit back and just take a look at them. And these are actually from a survey of the entire state that we've done. And don't want details about it by any means. These are incidents, average incidents just for counties, nothing much. But just look at how different the years can be. So here's 2002 and 2003. 2004, we're seeing some higher amounts. See that yellow? 2005, all green, all low. You see that, so that rating was 0 as compared with 2004. Look at this, 2006, 2007, low even with our survey and in that rating that was given. 2008, 2009, getting a little higher. Those circles are a little bit bigger in general. Okay, in 2010, if you're not sure, there's quite a high epidemic year within the state of Ohio for Fusarium head blight. And so that rating went up to a 6. But I just want to show you the overall general picture of what we mean by sporadic and what that looks like as you go throughout the different counties in terms there of just a general average incidence from another paper. All right, so if you've been in this talk for the last hour, you already know everything that I have up here, but I'll just go ahead and show it to you maybe a little different on a world map. We all know that this El Niño Southern Oscillation is sitting over here, and the other oscillation I'm going to talk about today is this NAO, which is that that North Atlantic Oscillation. As Clyde said, that affects his stuff in Florida, and we also found that affects what goes on in Ohio. So the other main thing I'm going to talk about is not only El Nino. We've seen El Nino 3.4 used by our first speaker, and we've seen some other representations of ENSO. The representation I'll be showing you today is called the ONI, which is the Oceanic Niño Index. All right, and we've all seen these maps, but we kept looking at different parts of the United States. So if you can't tell, I know it's not perfect, and if you want, I got it straight off of this website. Yes, I borrowed. And so we already saw, that El Niños had wet times down here in Florida, but what I want to draw your attention to is this little circle up here, dry. So El Nino actually produces drier conditions in what I'm looking at right now for the state of Ohio. And you can see that also would go into Indiana and to southern Illinois, it looks like too. And down here, the La Nina is really producing the wet conditions right there in that Ohio region. And so really the question becomes, the El Nino producing the dry conditions and the non-La Nina producing those wet conditions, do we see more fungal disease over these 51 years when we have these wet conditions? And do we see less fungal disease over these 51 years when we see dry conditions? And the answer is going to be yes, which was quite exciting when I started to realize that that was the answer. So this is the Oceanic Niño Index. As you've learned if you've been in here, we've got these top guys up here. When this is positive, that relates to an El Nino. When this is negative, that relates to a La Nina. And I just want to also point out that absolutely all of this data is freely accessible. And I tend to get it just literally from climate.gov, has links to everything, or just the Climate Prediction Center. All right, so now kind of into some mathematics. I started in published paper in 2012 that looked at this data using what we called a spectral analysis. So just a real quick overview of what that is. I'm not going to go into detail on it. It's all written up here, along with, by the way, an extra section of the paper to explain how to do this in SAS if you wanted to recreate or try some on your own. But the whole point of spectral analysis and what I did was took these up and down patterns that we see, these oscillations, and what you end up doing is essentially just fitting this, it's a combination of a sine-cosine curve to the entire pattern, so across all of those 51 years. Now, if you can't see, this right here, this has a periodicity that's very short, so a 2.3-year period, and it doesn't fit the data very well. Okay, but as we go and maybe look at some others, we're actually going to see that we can find some periodicities that do fit this data pretty well. But that's how, and especially that one right there, a period of 7.6 starting to look decent, and I just gave you some examples here. But that's the underlying theory of spectral analysis. You're essentially taking these sine-cosine curves, fitting them to your data, and seeing which ones fit the best. All right, so the new and sort of next method that I've been using past spectral analysis has been something called wavelet analysis. Now, wavelet does something a little bit different and gives you a little bit more information. So this is the ONI, and we talked about that before. With a wavelet analysis, you literally pick a wavelet. And by the way, there's a whole lot of literature on what wavelet to pick, what it should look like, and it's a conversation for another time. This right here is a representation of what would be potentially a Morlet wavelet. But what you do is you take that wavelet, and you see how good does the underlying data fit that wavelet, and then you move it. How good does that data fit that wavelet? And you move it, and you move it, and you move it. And then you scale it up. You make it a little bit bigger, and you see how good does it fit. So you see the difference between this and spectral analysis. The spectral took the whole data set at once. This allows me to look at it at each individual interval across the whole series. Keep going. All right, so another big information that we get out of this, which we've been talking about a little bit in some other graphs today, is who's leading who, and can you even tell? Okay, and by which one of these series leads or lags behind the other. And that we call, and more formally, a phase shift. And so I know you can't see this, but I have both of these on the same periodicity of 4.63 years. And if I blow that up a little bit bigger, this is essentially what it would look like. You would have the ONI here in blue, you'd have the FHB here in green. And if we say, well, the ONI to a positive So a high value of ONI, which is like the El Nino, to high levels of FHB, well, that's like 2.9 years. Not quite sure that's really causing anything. What I'm more interested in is this negative relationship here. And in fact, some of the work we did before had that even at a smaller interval. And so my more question is what we think. So remember, El Nino being high are drier times. So our drier times, the El Nino, helping to lead within that next year to lower amounts of the fungal diseases out in the field. And that's what we're seeing here. All right, so a couple more things. The wavelet analysis comes out with some nice pretty pictures. I don't want you to think that it doesn't also have good data behind it, but the pictures are greatly helpful. So what we have over here are some of those periods, and we hopefully get what that means a little bit. So where it's a little bit darker up here, the higher numbers simply means that it fit a little better. Lower numbers meaning it fit a little worse. Okay, so these places that have higher numbers that have circles are saying that's where that wavelet fit along your time period at that particular scale. So that's how big or small the wavelet was at that point. So the wavelet was crossing about 4 years here, and it fit pretty well between, here and kind of the mid 1990s. That's how you would interpret what we're seeing here. And we also see, this is what I like the most, is that FHB in Ohio has consistently been showing up every, I would say, 3 to 6 to 7 years. And even if you just look at the raw data set, or even just that first graphic, and you count years in between when it's high and low, you see that. You see that. So these right here, these pretty pictures, are results from the wavelet analysis. These over here are those same results, but results from the spectral analysis. And so how you would interpret these is to simply say, where is there a high amplitude? And that those higher amplitudes right here, those tend to be places where that model fit the data well. And so it explained, a more important amounts of the variability, which is something we're looking for in this particular graphic. I would say even more important, though, is this slide here, which we call wavelet coherence. And it's all about kind of the idea of an R squared. How related are these two series? And so what we see here is I've got a color scheme going from 0 to 1, very similar again to an R squared. They'd be highly coherent if they had a value of 1. And then I also have in here little teeny tiny arrows. You might not be able to see them very well, and maybe if you go back over this presentation, you'll be able to. But what these arrows are telling us is that idea of the phase shift. Okay. And then this result here is from the spectral analysis, again, showing high coherency at particular periods. The whole point here being that FHB tends to recreate itself again about every 5 years. These climate patterns that tend to hit again La Nina years about every 4 to 7 years. And that happened, and it was true when I first wrote the first paper in 2010, and now even adding in the 2011 to 2015 data, we're still finding those same results, and that trend did still happen. All right, I think my time is about up, so I'm actually going to go ahead and skip through, but I guess I'll show you quickly. You don't need that. So I was going to show you here also the SGB, and it's coming out very similarly. You see it also tends to be around that period of 5 years, and we already learned that the ONI was, and we do have some high amounts of coherency at those similar periods. The Northern Atlantic Oscillation was doing the same thing, and sometimes even a little bit better than the Oceanic Niño Index. Look at this, we have a coherency right up here at about 0.8. And so again, that's kind of like the idea of an R squared. It's how very much similar these two are behaving. All right. I won't, if you can't tell, it's like the only slide that actually had words on it, right? So if you want to read some conclusions, you're more than welcome to. Essentially what the conclusions say is what I've been getting at, that we are saying the La Nina years are producing wetter conditions in Ohio, which is leading to more fungal disease in terms of the Fusarium hebelite and the Staganospora. And again, This work it's young, it's fresh, and even the two methods I showed, the spectral and the wavelet analysis, honestly may or may not be the best way to be looking at this. And definitely, it needs absolutely a cohesion with the local environmental conditions, as Clyde, I think, did a great job of pointing out when he pointed out one side of the screen with weather and what you can predict from that, and the other side, what you can predict with climate. And I agree with everything that was on there. And that's all for today. Thank you very much. I don't know what time it is. All right, so it is 9:45, which means that our session time is up. I guess I did talk too long. However, I know I can stay for 10 minutes, and if my speakers can, if anyone has questions, either please feel free to come up, I would say, or we can stay in this format if not too many people leave. Are there any questions for myself or any of my other speakers? Then you're free to go. Thank you.